Hi, my name is Zane Hensel, and I will be discussing the use of Marx theory in determining the most efficient electron transfer rates in hexabromopluminate -4. So a little overview of what I'm going to be talking about. I'll be talking about the Marx theory, the equations that I used, results, and the conclusions that I came to. The Marx theory was originally developed by Rudolf A. Marcus in 1956. It is used to explain the rates of electron transfer reactions from an electron donor to an electron acceptor. He won the Nobel Prize in Chemistry in 1992, and it has a lot of different uses in biology and chemistry. The one I think is most profound is the charge separation in solar cells. The Marx theory can be shown on a graph, and the two species, the electron donor and the electron acceptor, can be shown as equations, and the equations are on the left. The theory states that the highest rate of transfer is when DC and DD are equal to each other. This is contradictory to what I found. These are some of the equations I used in my wave pattern analysis. I have my wave function, the Hamiltonian operator, the evolution operator, probability distributions, the evaluation of transfer, and if we solve for K, we can get the reaction rate constant. And then my lambda G and lambda E are shown on screen. So these are the two plots that I think show the most of the ones that I've seen. The offset or the difference in energy on the left is 0, and difference on the right is 1. And once these we can just say it from here. So on this one, we can see that the curve is a Gaussian shape, and it's all staying together, which means the electrons are traveling in a pack, so the probability of them being in the same place is high. But on the left here, we can see that the electrons are in 4 different states, and this is because the activation energy needed to get over the curve is too high for the electrons to do. I think this graph best shows the data, and you can see the electrons there in the blue. That is the -4 state, and this offset is -0.0148 hartrees. This is offset of 0, offset of 0.0074, and this offset is 0.0296 hartrees. We can see that once the electrons get to a certain place in the 0, they will all convert to this -3 state. And on where the offset is 0.0074, we can see that they actually transfer to the 4th reaction state, but they all come back to the -4 state in the end, which shows us that it is a reversible reaction. This shows the yield of the electron transfer. In this graph and this graph, which are the -0.0148 hartree and the 0.0296 hartree, we can see that the reaction only gets to about 3 to the -3rd, which is so small that nothing really happens. And this is because the energy wasn't high enough to get over the curve. But we can see in where the offset is 0, yield actually gets all the way up to 1, almost 1. And then where the reaction, or where the difference is 0.0074, gets up to about 0.5 and drops back down in a reversible reaction. These are the energy offsets that I was using. And then this graph shows where the energy offset was highest, which is at 0. This is because the P0, my initial momentum, was actually set to 0, which is contradictory to the Marx theory, which states that it should be around 0.06 hartree. But since the initial momentum was so low, the reaction doesn't really abide by the Marcus theory, stating that the DD and DC should be equal. The conclusions, we can see that the highest rate of electron transfer is 1.26 e to the minus 4 at an energy differential of 0 at a very low temperature. And where it should be is where DC and DD are intersecting. And this was actually where I found my highest electron transfer was DD and DA were 0. These are my references. Any questions?
Okay, please join me in thanking Zane.